We have a video here on identifying domain and range of a function. Identifying the domain and range of a function, you need to understand what a domain and what the range is. And so when we look here, you should know that the domain is the input values and it's also the x values. They're all one and the same. And the range would be the output values and then the y values. So if we were to have, say, a table here with the x values and the y values, and say this is 0, 1, -2, and we can go -10. And let's say this one right here is going to be say -5. Let's say we have this function here. Well, you know, since this is the x values, it's also the domain, and since this would be the y values, that would be the range. Let me draw a straighter line here. So you have input values and you have output values, the x and y's. Now in a table like this, you should know that 0, 5 can be written as a point. 0, 5, 1, 6 can be written as a point. 1, 6, and so forth. So we're looking at points like this. Well, in a graph, if we were to graph these, 0, 5 would be something like this. 1, 6, -2, 3, and -10, -5 would look something like this. And so there are 3 different ways to represent it. You can represent it as a table, if we're talking about domain and range together. You can represent those input and output values as a table. You can represent it as a set of ordered pairs, or you can represent it on a graph as points. And sometimes we like to connect those points to make a straight line. So you have to understand domain and range, you have to understand the definitions, and you have to have that part memorized. All right, moving on. There's one other thing, 2 things that I'm going to need you to know that we're going to be using. Some terms and phrases here, some vocabulary. So looking up here, real numbers. What are real numbers? Well, up to this point, you've only probably ever used real numbers in your work, but there are some imaginary numbers that you may be using in the future. So let's look here. It says the set of all numbers along a continuous number line. So I have a continuous number line here. So the set of all real numbers along a continuous number line, it includes rational and irrational numbers. All right, let's look at the diagram I have down here. Rational numbers. Well, rational numbers are, you know, fractions that repeat and fractions that terminate. And if we look here, integers are also rational numbers. Now, you know, you might look there and say, well, how can an integer be a rational number? Well, let's look at -2. Isn't it -2/1? So it's a rational number because it terminates. You know, 2.00, we can go on, but it terminates right there. So you notice here integer numbers have all these negative ones listed in it. But then integers also, you see the big green circle? The big green circle also encompasses 0, and it also encompasses 1, 2, and 3, the natural numbers. So integers are 1, 2, 3, and so forth. It does include 0, and it's all these negative numbers, and it keeps going down to -5, -6, and so forth. So that's what integers would be. Now, is -1.5 an integer? No, -1.5 is not an integer, but -1.5 would be a rational number, it would fit out here into the rational part. Irrational numbers are basically numbers that don't terminate and do not repeat. And when you look at their decimals, when you think about their decimals like that. Okay, so basically we will be talking about real numbers because let's look at some of these. 1, 2, and 3. Can we plot those on the number line? Well, there's 1, there's 2, and there's 3. How about 0? Can we plot 0? Well, right there's 0. And of course, negative 1, 2, 3, and 4. Negative 1, 2, 3, and 4. And what about 11 halves? Well, that would be 5.5. And what about 1.3? Well, 1.3 is somewhere about right there. 3.79 is somewhere about right there. And negative 4 thirds would be negative 1 1/3, which is somewhere about right there. Now, what about irrational numbers? Can we plot those on a number line? Pi is 3.14. How about right there? And the square root of 3, well, the square root of 3 falls between the square root of 4 and the square root of 1. The square root of 4 is 2. The square root of 1 is 1. And I know 3 is closer to 4, so that means it's closer to 2. So when I plot it here, I'm going to plot it somewhere closer to the 2. So, looking there, well, the square root of 5, well, we know the square root of 5 here would be larger than 2, because its square root of 5 is larger than the square root of 4. So, it's somewhere, oh, it's probably going to be a little further to the left than I had put it, but if you notice here, we're able to graph natural numbers, whole numbers, integers, rational numbers, and irrational numbers on this number line. That would be all the real numbers. And you notice that none of the points really come out here, none of them really come out here. Well, that's just because our examples in this diagram didn't go out that far. But we know that not negative 10. We know that let me get rid of some of this. We know that like positive 10 would be a natural number and negative 10 would be an integer. Positive 10 is also fits into the whole number and also fits into the integer part. Remember that big green circle encompasses the 10, and then the yellow circle, I'm calling them circles, they're not circles. The yellow part encompasses the 10 also. So positive 10 is a natural number, it's also a whole, and it's also an integer. And then it would also be considered to be rational. All right, so real numbers. So you basically have to think that if it can be graphed on a number line, it's a real number. And so we're going to be using that terminology in some future slides here, talking about domain and range. Another term, infinity, we're going to be talking about positive infinity and negative infinity. So if we look and we want to count 0, 1, 2, 3, and we say dot, 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 well, those dots just mean that the numbers keep going. 4, 5, 6, 7, and I probably don't need to keep writing all those, because if I just put dot, 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 you understand that it just keeps going forever. And when it keeps going forever, where does it keep going forever towards? Well, that's what we call positive infinity. There's the positive sign, and there's the, that is not a good looking infinity sign. And there's the infinity sign. So that means those dots keep going to positive infinity. Now what about in the negative part? If we go negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and so forth, where is that going to stop? Well, that's not ever going to stop because these dots tell me that it keeps going forever. So what we do is we say that goes to negative infinity. Counting those numbers down towards the negative part, we'll go to negative infinity. And so those are some terms that we will also be using. Positive infinity and negative infinity. Okay, now for some examples. It says identify the domain and range of the graphed function. So domain, remember, domain is going to be the x values. So let's take this one at a time. Let's look at domain first, and then we'll talk about range. So domain is the x values. Now, the x values, you know the x-axis goes left and right. So let's look at the x values. If I were to take, and if I were to plot this point right here, the function we're looking at is y equals sine of x. So this is a little bit different than the graph you're used to, because this point right here, you want to think of it as 1, 1, 0. But when we talk about y equals sine of x, if you can see here, this is actually pi. That point is actually pi. This would be 2 pi, and this would be 3 pi. So what is this point right here? What's the point? Well, that would be 1 pi. So you go 1 pi to the right and up and down 0. And how about this? You can put this in x and y. You can put it in parentheses too. And you can put this one in parentheses. So every single point on this graph you could put into an x and y format. Even the negative ones you can put into an xy format. So in thinking about domain, you need to think about what is the smallest x value you could possibly have. What is the smallest x value you could possibly have? Well, the graph keeps going in this direction. And we notice that it keeps going, and it's going to keep going in this same direction forever to the left. And when we talk about to the left, that's the x-axis. So if it's going forever to the left, that will be negative infinity. So we say negative infinity is less than x, and that's just going to be on the small side of the x value. Now what about the large side of the x value? So we notice that this keeps going, keeps going, keeps going, and it's never going to stop. So what's the highest x value you could get for this function? The highest x value you could get would be positive infinity. And so we've just used a compound inequality here. That just means two inequalities put together to describe this this domain. Now typically when we have this, we don't want to leave it in a compound inequality. We will say the domain is all real numbers. And why do we say that? Because remember, this is a number line, and if we go from negative infinity to positive infinity, this number line will cover all real numbers. It's part of the reason why I was discussing all real numbers at the beginning of the video here. Now the range is going to be dealing with the y values. So let's look at the smallest y value. If we look, this looks like the smallest y value. It looks like there's all of these. This is the smallest y value. So what is that value on the y-axis? Remember, the y-axis goes up and down. Here's the y-axis. So what is this value here? This value is -1. So -1 is the smallest y value. Then what would be the largest y value? Well, we can see here on the y-axis, that would be +1. And so then what is the range? The range, and it actually does touch -1, so we have to put an equal to sign right there. You may see the range written something like this, compound inequality that we have. Or you may see it written that says the range lies between -1, and +1. And it may say something like this: and does include -1 and +1. So what it's saying is -1 and +1 are part of the range, and then every number between them. Okay, that was the first example. Now looking here, domain and range. Here's the function, y equals the absolute value of x. So let's look at the x values, talking left and right when we talk about domain. So we notice that this function keeps going on and on forever in the right direction. So that means it goes to positive infinity. And then what's the smallest x value? Well, it keeps going on and on forever in the left direction. So that means it goes to negative infinity. So what's going to be the domain here? The domain will be all real numbers. The domain is not always all real numbers. It just happens to be in these first two examples. That's what it is. Now for the range, let's look at the range here. We know we have to have some values. So the range talks about the y values. That is the up and down axis. So it looks like right here is the smallest. Right here is the smallest y value because the graph lies above that. So that would be 0, and it does include 0 because it touches 0, so we have to put the equal to sign down below that inequality. And then what's the highest y value? Well, if we notice that this keeps going up, and this one here keeps also going up. So if it keeps going up and it's never going to stop, that means it goes towards positive infinity. You're probably not going to see the answer choice like this. You're probably going to see the answer choice that say the range. The range is all real numbers. All real numbers. It'll either say greater than or equal to, or it'll say at least 0. I'm going to say all real numbers greater than or equal to 0. The range is all real numbers greater than or equal to 0. And this right here is just information that you may use to help you collect what the domain and range are. One more, and then I'll let you try to work the last two out on your own. So if we look here, identify the domain and range. The domain here will not be all real numbers, like I told you before. The first two examples were, but this one's not. So let's identify the domain, which talks about the x values, which is the horizontal axis, the axis that goes left and right. So if we look, right here is the smallest x value, and we notice that it has a closed dot. If it has a closed dot, that means it does include 1. If it's an open dot, 1 is not a choice. And so, let's see, x. So the smallest value is 1. That would be, this is what it looks like if it's an open dot. But a closed dot means we have to include 1, so we have to put the equal to sign there. So this says 1 is less than or equal to x. Now, it keeps going in this direction. So what direction? It's going to the right. And will it ever stop in that direction? It doesn't ever stop in that direction. If it were going to stop here at 6, there would be a point like you see right here. Okay, so we know that it keeps going in this direction to the right, and so we know that would be towards positive infinity. So the domain here would be, the domain is all real numbers at least 1. When we say at least ones, that means 1 is included in that. Or we could have said all real numbers greater than or equal to 1. That would have also been another option here. And for the range is talking about the up and down. So let's look at the range. If we note this keeps going in the down direction forever, it keeps going down forever, we know that's going towards negative infinity. And if it stops right here, that would be positive 4. And it does include positive 4, so we have to put the equal to sign there. So the range here, we will say it is all real numbers less than or equal to 4, or we can say all real numbers at most 4. I think I like less than or equal to better. Sounds better than at most. But both of them do mean the same thing. And so that would be the domain and range for that function. I would like you to pause this part of it and then identify the domain and range for yourself, and then I will stroll through it quickly with you. All right, so I'm looking at the x values. I know it keeps going in both directions. It goes left forever towards negative infinity. It goes right forever towards positive infinity. So the domain is all real numbers. And the y values, well, right here is the largest y value. And I'm going to say the largest y value, somehow I don't know if that is a horizontal line. It does look more horizontal than it looks more horizontal than the last one. So I'm going to say it's halfway. And between there, well, if this is 2, this would be what? 1/2, 1, 1.5. Nope, that's not what that is. So if this is 2, this is going to be 0.4, 0.8, 1.2, 1.6, 2.0. So if this is 0.4, this one here, 0.8, and this one here is 1.2. Right there is halfway between 0.8 and 1.2, which that would be 1. So the range, the largest value for the range is going to be 1. The smallest value, we know it keeps pointing down. It keeps going down towards negative infinity. So the range is going to be all real numbers at most 1, or all real numbers less than or equal to 1. That would be the range. And this last one, go ahead and pause the video here, hit play when you're finished, and identify the domain and range. If I'm looking, it points towards positive infinity and it points towards negative infinity. That's left and right because I'm dealing with domain first. So once again, this is a super easy one that says all real numbers for the domain. Now the range is a little bit different because the lowest y value is -3, and it keeps going up in both directions. It keeps going up in both directions. So that would be the range is all real numbers greater than or equal to -3. And that's the domain and range of that function that you see on the graph. That's all we have on domain and range. Let me know if you have some questions.